Yeah, so let's start with a small about complex numbers. So look at this. Look at this complex number. Write down its Cartesian form and polar form. So I can give you 3 minutes and we can discuss together. And here's the Euler's formula in case you need it. Okay, so for the Cartesian form, do you have any ideas? We have it's e to the power of j theta is a standard complex exponential multiplied by 1 plus j. So this is close to the Cartesian form already, but it is multiplied by a complex number. So what is the, do you have any ideas on this? Yes. Okay, so what is the main idea for doing that? The main idea? Right. So you distribute this. Okay. Mm-hmm. Right. So this is yes. Mhm. Right. And then everything is in a kind of Cartesian form. Yeah. And then just do the calculations and rearrange all the terms. So you find out all the real parts. I think this is real. And here, this is imaginary because we have J here. Here we have J times cosine theta should belongs to the imaginary part. And the last term we have J squared times sine theta, but J squared is -1. So we have this one as the real part, and then the rest of the two terms. As the imaginary part. So this is the standard Cartesian form. And these are the real and the imaginary parts. Okay, now what about the polar form? Do you have any ideas? Yes.
Yeah, so I just did r is equal to square root of cosine theta minus sine theta squared, cosine theta plus sine theta squared, and then the angle is arctan cosine theta plus sine theta divided by cosine theta minus.
Okay, that's a little bit complicated. So tell us about your main idea. So what is your
So to get the magnitude,
so
you square the real part, you square the imaginary part.
Okay.
Then
So
square the-
did you get that from the Cartesian part?
yeah,
And by and then calculating out the
yes.
okay. Yes, that's definitely that is one option. Yes. So once we have this Cartesian form, we can leverage this right here. We can leverage these two transformations to calculate the magnitude and theta for the polar form. So you have this r equals to square root of the real part plus the imaginary parts. So well, this one and the theta, okay. And theta is arctangent imaginary divided by the real. And we will plus pi if the real part is negative. So we have an indicator here that looks at if the real is negative. And actually, you can further simplify this R by using the equation that square of sine plus square of cosine equals to 1. So this actually equals to, well, you see, you have cosine square plus sine square minus the cross term. And here you have sine square plus cosine square plus cross term. So the cross term will get canceled out. And so you have basically you have 2 times sine square plus 2 times cosine square. That gives you square root of 2. So that is the R. And theta is okay, the notation is a little bit confusing. Let me change theta to be another angle, alpha, because theta is used in this problem. So the phase alpha depends on the specific value of theta. Okay, and this is one approach. Once you get the Cartesian form, you can use this one to get polar form. The second approach is that by looking at this form, because we are looking at the polar form, so this is already in the polar form. So it might be very convenient to transform this part to the polar form. But because this part is a standard Cartesian form. So once you transform that into the polar form, you have a product of 2 polar forms, and that is easy to calculate in the product form. And for this one, the polar form is easy to get. So you just, again, apply in this transformation formulas. You get the magnitude is square root of 1 plus 1. So you have square root of 2. That's the magnitude of this part. And the phase is, so here the imaginary part is 1. The real part is also 1. So looking at phase formula, you have arctangent 1. And this one, the real part is positive. So we can ignore this part. So you only have arctangent 1. That gives you pi over 4. Okay. And then you can get the final result is theta plus pi over 4. Theta plus pi over 4. And this one looks simpler than the alpha here, although they are equivalent. Okay. So we can see that we have multiple approaches to deal with the complex number in general. So in practice, you need to do a lot of problems in order to get some intuition of which approach works the best in practice. Okay, so last time we end up here. So we have this Euler's formula, which tells that the standard complex exponential can be decomposed into such a Cartesian form. And with this, remember that sine and cosine functions, they have very nice representation in terms of the complex exponentials. So in a homework or in a general problem, whenever you see a pair of complex exponentials and one is conjugate of the other, always remember that this pair of complex exponentials can be simplified into sine and cosine. And in many cases, that helps a lot in simplifying the problem. And on the other hand, we have shown that, so this is the inverse Euler's formula. We can write cosines in terms of complex exponentials. And the other way that we may use a lot if you take the communication course is that cosine is the real part of this complex exponential, which is basically by the definition of the real part. And then we can use this to rewrite. In practice, we always, in many cases, we deal with the very basic signal, which is the cosine wave. Well, this A is the magnitude, is the amplitude of the signal, A times cosine omega t plus phi. Omega is the angular frequency, phi is the phase. So this is a standard cosine signal. And we can use, for the cosine part, we can apply the inverse Euler's formula to decompose it into this form. And then what we do is that we put all the constant terms as the coefficient. So all the terms that do not depend on the time t are regarded as the coefficient. And then we have this EJ omega t. This is a standard complex exponential signal. This one plus is conjugate term. So basically, any cosine signal can be regarded as, can be decomposed into two complex exponential signals. One has a frequency omega, the other has frequency negative omega. And we will see that this is basically the idea of Fourier transform later. And by utilizing the second characterization of cosine theta, we can write this cosine signal in terms of the real part of this complex exponential signal. But in this course, we will use the first one, the first inverse formula, very often. So whenever you see a pair of these complex exponentials and they are conjugate with each other, always think of cosine or sine signals. Okay, that's the first lecture where we basically review all the complex numbers, properties of complex numbers. So are there any questions regarding the complex numbers? Yes. Okay, yeah, that's a great question. So the question is, what if we got negative pi over 4 here? So then we can look at this example. This will make that phase term to be negative pi over 4, right? So by the same approach, we got J. And now if you apply, okay, let's look at that. Following this formula, now for this one, the imaginary part is -1, the real part is 1. So you have arctangent -1. So you have arctangent -1. And in this case, x is still positive. So we can ignore the second part. And we know that arctangent -1 is negative pi over 4. We only have, it is unique. So you end up with square root of 2 of EJ theta minus pi over 4. Yeah, but later we will see that this complex exponential is a periodic signal. So basically, EJ theta equals to EJ theta plus 2 pi. Why? Because by the Euler's formula, e to the power j theta is a cosine plus j times sine. We know that both cosine and sine have period 2 pi. So when you sum them up, this complex exponential also has a period 2 pi. So if you apply this property, this is equivalent to, you can add a 2 pi inside, so that becomes theta. 2 pi is 4/8 pi. So that is 4/7 pi. So they are equivalent actually. Yeah, you can write either one, but usually we keep the phase term between negative pi to pi, so that you don't get a number that is bigger than pi here. Yeah, so this one is more standard. But either way is acceptable. Yeah. And to prove this, you can just apply the Euler's formula. You have cosine theta plus 2 pi plus j sine theta plus 2 pi. And we know that cosine and sine, they are periodic signals with 2 pi. So this is cosine plus j sine. Okay. Okay. Are there other questions? Yeah, if no, let's go to the lecture 2. Okay, so this is the first lecture where we start to talk about the signals, the first component of this course. So we will talk about different categories of signals. We will categorize signals in different ways, following different standards. So that's the first part, signal classification. And then we're going to talk about how to calculate the energy and the power of a signal. What is their definition? And after that, we will introduce some basic operations, transformations of signals. And that is it is like a addition, multiplication of numbers there. And in the end, we will list numerous types of signals that we will frequently use in this course. So basically, this lecture is a very, very important lecture for this course. Okay. Yeah, we have defined this continuous time signal in the introductory class. Well, for a continuous time signal, we can denote it as xt or yt or any other letter you like. But the definition is that the variable t can take any continuous real values. So for this continuous signal, by convention, we call it continuous time signal. Okay, so this is defined as a function of a time variable. Okay, so basically, if we want to look at the value of the signal at a particular time, t, then basically you just look at x, evaluate at t, xt. And also we have continuous, so we have this discrete time signal. Well, the definition is almost the same. The only difference is that now the variable is only indexed by discrete numbers, integers. So basically, a discrete time signal is a sequence of samples. Basically, a vector, a long vector. And we usually write discrete samples as x bracket of n. So we use bracket to distinguish from the continuous part. And we always use n to index the discrete time steps instead of t. So because it is discrete, so this n can only take integer or some discrete values, but usually we take integers. It could be positive integers or negative integers. So as an example, we will discuss this later in one of the lectures. For a discrete time signal, we can sample the discrete time signal at some sampling period. oh, sorry, we can sample a continuous time signal at something period to generate a discrete time signal. So here's the, we can visualize this process, sampling process. So we have this continuous time signal xt. Okay, and now I want to, because if I want to record this signal in a computer or digital device, I have to discretize it. So therefore, a standard approach is that I take samples of the signal periodically at a certain frequency. And assuming that I'm sampling this signal with a sampling period t, that means for every t seconds, I will take one sample of the signal. So now I'm looking at these discrete points. Okay, I'm looking at these discrete points. And this signal can be, now these discrete points, they form a discrete signal. And I can say that this discrete signal is, the value of this discrete signal is the corresponding value of the continuous signal evaluated at the nth period. Okay, to be more specific, let me right. So we are sampling this continuous signal as 0t, 2 times t, 3 times t, 4 times t, 5 times t. And then these are the discrete samples that we generated. So specifically, now this is x0, this is x1, this is x2, and this is x5. So you can see the nth entry of this discrete time signal is basically the value of this continuous time signal evaluated at n times the period t. Therefore, we build a relation between the discrete signal, between the continuous signal and the sampled discrete, periodically sampled discrete signal. So this is how you describe a sampling process. You have a continuous signal xt, and you sample this signal at with a sampling period capital T. So that will generate such a discrete signal xn. So here n is any integers, any integer. Okay, so this is the discrete time signal. So we can generally classify the signal in this way. Either it's continuous or discrete time. Okay, and this is a very, next we will talk about causal signals. This is a very important class of signals, because later we will use this to define causal systems. But here the definition is very simple. If a signal is causal, then the signal can only exist in the positive part. So signal can only be non-zero when t is greater than or equal to 0. That means for all the t that is negative, less than 0, the signal is always 0. There's no signal in the negative part. Right, so for example, and this is a causal signal. The signal only exists in the when t is greater than or equal to 0. And once we have this definition, then the non-causal signals means they are not causal. That means they violate the definition of causal signals. So if the signal is non-causal, that means there must be some signal exists in the negative part. Right. So there exists some non-zero signal in the when t is less than 0. So this is non-causal. Anti-causal is the opposite of being causal. So anti-causal basically means the signal can only exist in the negative part. So these are just the definitions. So the signal can only exist in the when t is less than 0. So when t is greater than 0, it has to be 0. Signal has to be vanishing. So this is the definition of causal signals. And next we talk about complex signals, and this is very simple because we just reviewed the concept of complex numbers. So we can generally, in this course, all the signals that we discuss are complex signals, meaning that we write ZT representing a complex signal, which is basically writing out its Cartesian form. We have a real part xt plus j times the imaginary part yt. So basically a complex signal consists of two real signals. One is the real part, the other is the imaginary part. It's exactly the same as complex numbers, except that we now have a time index t to index this signal. And then we can just follow this convention to define continuous time complex signals and discrete time complex signals, depending on whether this index is continuous or discrete. Okay, so everything we discuss, every number, every lowercase letter that we wrote in this course represents complex number or complex signals. So everything is generally complex. Okay, so next we will introduce the signal energy and signal power. So this is related to the homework problems. So given a signal, either continuous time or discrete time, but we can look at continuous time signal first. Given a continuous time signal, how do we define its energy? Okay, the energy is defined as follows. So let's look at continuous time signal first, xt. The energy we write as capital E subscript s, meaning the energy of x, is defined as, here's the definition. I'm looking at the magnitude of this signal, raise it to the power of 2. So if you take a circuit course, you know that something to the power of 2 represents the kind of energy of this current or voltage signal. And because it is a signal, I'm gonna because we are looking at the total energy, so I'm gonna integrate in this power 2 over the time t from negative capital T and to capital T. And then I'm gonna push this integration interval to the infinity so that I can accumulate all the energies of this signal span over the entire time domain. But sometimes we just write from negative infinity to positive infinity. Okay, they are equivalent. So the critical part, okay, I need to remind you that here we're looking at the magnitude of the signal to the power of 2. So in general, xt, again, is a complex number. Xt is a complex signal. So if you look at xt, it is a complex number. So complex numbers, we talk about its magnitude in the review lecture. So we can calculate its magnitude. And the magnitude is a real number. So you can raise that real number to the power of 2 and do this integration. So this is the magnitude of xt. So if a signal has finite energy, so by this definition, we can calculate the energy of any signal. If the energy is finite, then we call this an energy signal. So the second definition is for discrete signals. We can also similarly define the energy for discrete signals. So for discrete signals, we don't have integration anymore because everything is discrete. So we just sum up all the squares of the signals at those discrete time indexes. So we just sum up instead of integration, we sum up all the square of the magnitudes of the signal over all the discrete indexes. Okay, again, we are looking at the magnitude of this complex signal. So in order to compute the magnitude, you need to write it in either the Cartesian form or the polar form, depending on the specific signal that you are looking at. So it is not the real part. Okay, the magnitude is not the real part of complex signal. So many students, when they first learn about this concept, they always mix this with the real part of the signal. The magnitude is not the real part. Okay, so this is the definition of energy. It's very, very intuitive. So we basically sum up all the squares of the magnitudes of the signal over the time domain. And following these formulas, you can calculate the energy of any signal. And the one related concept to energy is the power. Once you have the energy, we can define the power. So that the energy characterizes the total energy of a signal over the time domain. But when we talk about power, this actually represents the average of the signal energy over the time domain. So it is more like an energy density. So the power of a continuous time signal is defined as, so first of all, I'm looking at similar to the definition of energy. I'm looking at the energy of this signal accumulated over an interval from negative t to capital T. And then I'm going to divide it by 2t, which is the length of this interval. So I'm actually looking at the average energy. So I'm distributing this energy collected from this interval by the length. And then I'm looking at the limit. Okay, so therefore you need to calculate a limit going to the power. So you fix any capital T and calculate this average energy first, and then push this capital T to the limit. So that is the power of this signal. And similarly for discrete signals, we have a very similar definition. So we are summing up the signal energy over an interval from negative n to capital N, and then we are dividing this by the total the length of the interval. But now we are looking at discrete points. So between capital N and the negative capital N, we have 2n plus 1 points. But including the original point, that's where we have the plus 1, additional plus 1. So the total length is 2n plus 1. So we will divide this by 2n plus 1. And then we push capital N to the limit. And then we will call a signal with finite power a power signal. Just a definition. Okay, and here are two comments. The first one is that a power signal has infinite energy. So what is a power signal? A power signal means the signal power is finite. And this statement says that a power signal has infinite energy. So what is the argument for this, for proving this? A power signal means that this limit is finite. Well, if you compare this with the definition of energy, right? Compare this with the definition of energy here. You can see that in the power, we divided by 1 over 2t. In the energy, we did not. So if this is finite, then you can say that informally, you can say that this energy is, as t goes to infinity, right? We are dividing this part by 2t, and t is going to infinity. So if this is finite, then the energy must be, then this part must be infinity. Okay, let's try to be more rigorous. Okay, power signal has Okay, what this sentence says is that if Px is finite, right? Px finite meaning that this signal is power signal, the definition. If the signal x power is finite, then Ex is infinity. Why is that proof? Suppose Ex is finite. And let's prove by contradiction. Suppose it's finite, then Px, Px is limit 1/2t integration negative t t. Well, this part is the energy, right? Suppose energy is finite, meaning that this part, as t goes to infinity, is finite, right? So this is finite, but as t goes to infinity, divided by 2t, this 2 times t goes to infinity. So you have a finite divided by infinite. So that gives you 0, which contradicts with your assumption that this is a power signal. Yeah, I should probably say that this is strictly greater than 0. Yeah. If the signal has a strictly finite power, then the energy must be infinite. So the intuition is that the power is kind of an average energy over the entire infinite time domain. If this average if this average energy is strictly positive, then you multiply by the entire length of the time domain. That should accumulate to infinity, right? So that's why the energy must be going to infinity. Yes. Okay, so this is a proof by contradiction. So what we are doing, we are assuming, so we want to prove that the energy is infinite. So the logic here is that we prove by contradiction. We assume the conclusion is wrong. We assume the energy is finite. Then we show some contradiction. So that means it has to be infinite. Right. So under this assumption, if the energy is finite, then this part, by definition, this part, the limit of this part is the energy. So this part has to be finite. Yeah, and then we are letting t goes to infinity. So this denominator is going to infinity. Yeah, we have a finite number divided by something going to infinity, so it has to be 0. Yeah, but the intuition is basically that when the average energy is strictly positive, the accumulative energy is going to infinity. And following the similar logic, the second statement is also easy to understand. It says that an energy signal has 0 power. Now, what is energy signal? Energy signal means that the total energy that we accumulated over the entire infinite time domain is finite. If the entire energy is finite, then once we distribute this finite energy over the infinite time domain, then the power has to be 0, right? This power is defined as distributing the energy over the entire time domain. So this capital T goes to infinity. So if the energy part is finite, when you distribute that over the entire time domain, it's going to be the average energy is going to be 0. And the power is basically the average energy. Yes. I think this applies to both continuous and discrete. Yeah. So the discussion would be the same, right? So it's all about the difference between. So if let me see. So if you have a right, so it applies to both discrete because it has nothing to do with the. You can replace the integration by summation and saying that if you look at the last statement, right, if a discrete signal is an energy signal, that means this part is the energy part. This finite summation is this summation is finite as the capital N goes to infinity, and then you are dividing this total energy over the entire discrete time domain. And for the discrete time domain, the overall length still goes to infinity because we have infinite integers. So in the end, that will give you 0 power. So the discussion would be the same. Right. So this is how you calculate energy and power. So in the end, you will need to do this part first. You will need to calculate this integration or the summation part first, and then doing the other part. Okay, so we have some here. We have some examples of continuous time signals, and I would like you to classify these signals into power or energy signals without calculation, just by looking at this signal and follow from the intuition. So energy signal means that the energy of the signal is finite. Power signal means that the power of the signal is finite. Okay, let's look at one of the example first. How about the second one? It's a rectangle signal, which is pretty simple in this case. So let's think about for this signal. Okay, so first of all, this is a causal signal, right? By definition of causality, the signal only exists in the positive domain. Okay, for this rectangle causal signal, is it an energy signal? Or equivalently speaking, is the energy bounded or not? What is the definition of energy is here? Is the integration of this magnitude square over the entire time domain. So intuitively, do you think it's a yes? How about energy? Is it an energy signal? Right, right. So yeah, so it is not an energy signal because the signal goes to will last forever, starting from 0. So when you do this integration, okay, it's going to diverge. Okay. And for the power, so is it a power signal? So the energy goes to infinity, right? But how about the power?
Power would be finite because there's infinity.
Right. But then you need to make sure this infinity divided by infinity, you still get a finite number, right? So I think, yeah, I think that part you need to do some calculations to get a result. But this signal is pretty simple, so we can do a quick calculation following the definition of power. Okay, here's the definition. I'm gonna I'm gonna follow this. Okay, what happened? Yeah, I'm gonna follow this definition. So Px is limit. Now here's the thing. Okay, let me first draw a graph here to help me. Okay, I will draw it. Yeah. So I will look at negative t to t. Look at this interval. So the power is limit 1/2t integration negative t to t. But what is special is that if you look at within negative t to t, only the signal only exists between 0 and t. So I can actually integrate over 0 to t only. Okay, because the signal only exists in the positive part. And between 0 and t, the signal is a real signal. So the magnitude is basically the absolute value. And the magnitude is 1. So it's 1 square dt. Okay. So this is a real signal, very simple example. So work this out, integration 1 dt, that gives a capital T. So this one, very simple integration, is capital T divided by 2t. And then you can conclude that this limit is exists equals to 1/2. Right, so the power is 1/2. So the power is 1/2. Okay. Then looking at the first example, is a diminishing, again, it is a causal signal, but now it is a diminishing, and it diminishes geometrically fast. It's e to the power of negative t. So by comparing the first and the signal with the second signal, so first of all, for this signal, does it have a finite energy? The signal diminishes very fast, geometrically fast, very, very fast. So when you accumulate the square of the magnitude over the entire domain, is it finite or infinite? Finite, right? Because the integration of this e to the power of negative t over t is finite. Yeah, but intuitively, because the magnitude diminishes exponentially fast, so it's finite. Right? So Ex for the first one, energy is finite. Now, what about the power? What about the power? We have this. We have that statement of energy signal has 0 power. If the energy is finite, then the power is 0. Because you for the power you need to distribute this finite energy over this infinite time domain. So the power of the first signal is 0. Okay. Therefore, the first signal is an energy signal, not power signal. The second signal, not an energy signal, but it is a power signal. Okay. We just calculated power is 1/2. Now, how about the third one? It is a causal signal, but the magnitude is linearly increasing in the positive domain. So first of all, talking about its energy, does it have finite energy or infinite energy? Infinite, right? Because the magnitudes go into infinite. So when you integrating that, must be going to infinite. Okay, so now we have a infinite energy. So the power part is a little bit tricky. We need to calculate the power part to figure that out. So again, we follow the power definition. Here's the figure. So following the definition of power, we are integrating it's 1 over 2t. No, looking at negative t to t. But the signal only exists between 0 and t, so we only have 0 and t here. And this equation, line equation is xt equal to t. Xt equal to t. So we are looking at t square dt. The, the signal is t, so t to the power of 2 dt. And doing this, calculating this integration, the t squared dt, that what we have is a t cubic over 3 evaluated at 0 and capital T. So this gives capital T cubic over 3 over 2t. Right, so that's the integration. So you can see that the numerator goes to infinity much faster. So we have infinite power. So we have infinite power here because the magnitude diverges very quickly. Okay, yeah. Yes. If the power is finite, the energy has to be infinite, because the average power is basically the average energy. If the average energy is finite, the total energy over the entire time domain is going to be infinite. But this example shows that if the signal is very, very strong and the amplitude diverges to infinity very quickly, then the energy is infinite, and at the same time, the average energies can also be infinite if the signal diverges rather quickly. Yeah, faster than, especially faster than 1 over capital T. Yeah, then the power can still be infinite. Okay, now we have this fourth example, cosine signal. And without any calculation, so tell me, is the energy finite or infinite? It is a periodic signal. It has infinite remaining periods. So the energy is basically, collecting all the pieces of energies in every interval. Right? So do you think it's finite or infinite? Finite energy or infinite? Why is that? Yeah, it's not diminishing. The periodically goes back to 1 and -1. Yes.
Would it be finite because it
That's a good point. But and then you look at the definition of energy. Is the power of 2. Yeah. So the when it has negative amplitude, the energy is still positive. Right? When we talk about energies, it is always positive. Yeah. So basically, if you look at every half period, look at this positive half period. If you do that integration, it's going to give you some number because you believe this area is not zero, right? It's something strictly positive. And then looking at this half period with negative amplitude is the same thing because this power of 2, now this integration is going to be non-zero. So in every half period, you always have some small part of energy there. So when you accumulate this over the entire interval, you got infinity energy. You got infinity energy. But doing this mathematically, this is how you calculate that. So you have this. Yeah, I think this is a periodic signal. Let me see. Yeah. Right. So it's cosine omega t. I should write now the magnitude to the power of 2, but now cosine is just a real number, so we can just ignore that. And then we have this cosine squared theta is we have this equation. Cosine squared theta is cosine 2 theta plus 1 over 2. And you will also use this a lot often in the calculations. It is good to remember that. So you have cosine 2 omega t plus 1 e dt. And it is infinite because you have this part. This constant part will give you infinite value. And this cosine part is a periodic signal, so it will get canceled out periodically. So overall, this energy is infinite. Goes to infinity. And then we look at its power. So because it has infinite energy, so the power could be possibly be finite or infinite. We need to do the calculations. Right, so this is the definition of power. And for simplicity, naturally, we can just look at the one period. Oh, wait, let me. We can just look at one period. So it's negative pi to pi. But because this signal has But maybe I can, yeah, I think I can make it general. So let's consider anything. This t could be anything, but we can still do this integration. Okay, let's do this carefully. So we just uh, following this equation, right? We just showed this one. So we just copy it here. Cosine 2 omega t plus 1 over 2 dt. And then I'm gonna look at so it's 1 over 2 dt taking integration. Now it's 1/2 times t evaluated at capital T and negative T. So that gives me this one. So that's the constant part. The other part is right, and I can multiply this by 2 omega. Okay, so it's basically 2 omega t divided by 2 omega. Okay, so keep going. This is 2 capital T. So we have capital T here. And this is 1 over 2 omega. Now this is sine 2 omega t evaluate at negative T and T. Right. So we just, okay, continue. This is T divided by 2T is 1/2. So the first part we have a limit, but what about second part? Because sine, okay, sine 2 omega capital T minus sine 2 omega negative capital T. The sine function is an odd function, so we have 2 times sine of 2 omega capital T. Right. So it's a minus sine negative 2 omega capital T. Okay, this get cancels out. Yeah. 4 omega. So it is from here. It's cosine 2 omega t, d 2 omega t, right? So, where is that additional 2? So here I'm looking at, from here. Oh no, so we are starting from here, right? We're starting from here. And this cosine square equals to this one. Right, so yeah, and then we have 1/2 here. So 1/2 goes to this one. No, I'm still keeping the integration here. Right, so this is integration cosine 2 omega t over 2. Oh, yeah, yes. Oh, now I got you. So yes, I multiply 2 omega here, so I should divide it by 2 omega. So this is 4 omega. Yeah. Yeah, thank you for pointing this out. Yeah, 4 omega, 4 omega. Right. And this gives 2 times this one, the 4 omega. Right. So we still have 1/2t outside. So it's 2 times sine 2 omega capital T. This is this part divided by 4 omega here, denominator, times 1/2 capital T outside. Okay, so looking at this limit, what is the value of this limit? On the numerator, you have something 2 times sine 2 omega capital T. Now capital T goes to infinity, but it is inside the sine function. Denominator, you have 4 omega times 2 capital T. So the denominator definitely goes to infinity. Capital T goes to infinity. What about the numerator? Yeah.
It would perhaps many classes before it's negative.
Right, but if you look at this sine wave, right, the magnitude is always between -1 and 1, right?
Yeah.
Right. So the numerator should be bounded, right? No matter how no matter how big this capital T is, sine is always bounded between -1 and 1. So the numerator is always a finite number, and the denominator goes to infinity. So this one is 0. Yeah. So in the end, you get power of this sine signal is 1/2. Right. And then, so this is how you did you should do the homework. Following the definition, write down the calculations, and be careful with this because in the homework you may deal with complex signals. Here we are looking at real. And very quickly for the last one, we modulate this sine wave by an exponential wave. So it's multiplied by exponentially diminishing signal. So because of that part, because this exponential diminishing part, the energy of this signal will be finite. Okay, because the amplitude is diminishing drastically. And then because of the energy of this one is finite, so the power has to be 0. So that's a direct consequence. Okay. Okay, so these are the examples of continuous of the power and the energy. So you can start to work on homework 1. Most of them should be available. And next on Thursday, we will go over more examples on the power and energy. Yeah, just integrations. Okay. Okay, so I will stop here. I'll see you on Thursday.